right, hello. So in this lesson, what we're going to be discussing is properties of summation notation. Now, in the last lesson that we covered, we introduced the idea of what sigma was. And it's a way of kind of consolidating the process of, taking the sum of a lot of numbers in sequential order. Now, remember, sigma is really just a way of demonstrating, okay, well, the index number at the bottom is the first term that we start adding with, and whatever the index number in the top will be the last term that we add, and everything in between is also included in those, in the sum of whatever you're looking for. So here, these are the first 5 properties of summation. Now, the first one and the second one are actually pretty similar to each other in the fact that, in the first property that you're seeing here, obviously the index number at the bottom is a 1 because, generally speaking, especially in a generic term like this, we're going to start with 1. Now, obviously we don't have to, but that would be something that we specify in a particular problem. But this is just kind of generally for every summation that we see, we're going to start with 1. And the index up at the top, n, well, that just represents some wherever we stop, whatever that number happens to be. It could be any number that we want it to be. And c is just a constant. Well, n represents the number of terms that we are going to be putting in to be multiplied by whatever that constant number c is. Now, what you see at the beginning of the second property is very similar, but instead of saying n, we're saying a sub k, which is basically the same thing. Now, the difference between what we're seeing in 2 is that that constant number has been taken out, and the way you read it is you say c multiplied by whatever the sum of this other sequence is. Now let me just give you a brief proof of why that works. So let's say we have a summation where I start with 1 and I stop with 5, and I'm going to say 3 for my constant number. Okay. Well, what this winds up telling me is I'm going to say 3 times 1 plus 3 times 2, and so on through 5. Oop, 3. I said 5, so I wanted to write 5. Can't talk and write at the same time, apparently. 3 plus 3 times 4 plus 3 times 5. Well, what we're seeing here is 3 is being multiplied to each of those numbers. Because 3 is being multiplied to each of those numbers, we can use the distributive property to take 3 out and just say in parentheses 1 plus 2 through 5. Okay, so we're taking the sum of whatever of 1, 2, 3, 4, and 5, and they're going to be multiplied by the 3, so that gives me, as a final summation notation, I can say 3 multiplied by whatever the sum of the first term through the 5th term times whatever k happens to be, where you're substituting those numbers. So that's kind of where the that second notation comes from. Now the third notation is going to be one that we're actually going to start with. The fourth one we're really not going to be seeing a whole lot of in our curriculum, but it's there for general purposes. What that third notation is telling you is this is where we're going to be substituting some actual sequence where we say, like, 4 times k or 4 times x or whatever, plus or minus 3 or something like that. And we can actually break up the first term and the second term and take the individual sums of those things and then combine them, and that will give me the sum of the entire sequence. So let's go ahead and take a look at our first example here. Again, this is going to kind of take into account, it's going to be working really with the first, or with that second property of sums and the third property of sums at the same time. because 2 in the sequence is being multiplied by however many numbers that we wind up putting in there. So the terms that we're going to be adding are the first term through the fifth term. So at some point, what I would do is I would substitute the 1 through 5 in for k, and it would have to be multiplied by 2. Well, that 3 isn't being multiplied by k, so let's see how this works. Okay, we're going to I'm going to write it out as s instead of sigma of 5. And using the second property, okay, I would essentially be able to distribute that 2 out and be able to multiply it by the sum of 1 through 5. So that's what I'm going to write here. 1 plus 2 plus 3 plus 4 plus 5. Okay, well, since I'm subtracting the 3, I'm going to say minus 3. Now, if there was another variable on the 3 itself, we would have to substitute the numbers 1 through 5 again, just like we did for the 2. But since 3 is essentially a constant number, all we're going to wind up doing is multiplying it to whatever the last number is here, in this case 5. And here we'll say 2, and the sum of 1, 2, 3, 4, and 5, that is a 15. And then we'd say minus 3 times 5 is 15. So this gives me 30 minus 15. So the sum of the first 5 numbers of this expression, or of this sequence, I should say, is 15. Okay? And the other way of testing it is you could actually substitute the numbers, 1, 2, 3, 4, and 5, multiply the 2 times the 1, subtract 3. We'll multiply the 2 times 2, subtract 3, and so on. And whatever those 5 individual numbers are, when you add them up, they will still equal the number 15. So let's take a look at another one where we're kind of saying, okay, well, how can we use that? Okay, that last number now no longer it's just a number by itself. It's a number times a variable. Well, let's see what that does. So we'll still use the idea of we're using that second term or that second property and the third property at the same time, where I can take the 5, distribute it out of the overall sum, and multiply it by whatever the first 4 numbers squared are. So because that first k has a squared on it, the 1, 2, 3, and the 4 that I substituted into these parentheses have to be squared, because that's what I would do if I substituted them into the problem. So 1 squared plus 2 squared plus 3 squared and plus 4 squared. Now I'm going to say plus a 3 because that's what we have in the sequence. Now again, using that second property, that 3 essentially is going to get multiplied to a 1. The 3 will get multiplied to the 2 and the 3 and the 4. Well, that means we could distribute that out like what that second property says. And I can just put the 1 plus 2 plus 3 plus 4 inside of the parentheses and go from there. So I'm going to square all of the numbers and then take the sum of them in the first parentheses. So 1 squared plus 2 squared plus 3 squared plus 4 squared. Those are all going to equal the number 30. And so I'm going to say plus 3, and 1 plus 2 plus 3 plus 4 is a 10. So that gives me 5 times 30 to be 150, plus 3 times 10 is 30. So the sum of the first 4 numbers of the sequence that we were given is going to be 180. And you would get the exact same thing. Again, if you want to check it, take 1, 2, 3, and 4, substitute it into the expression each time, evaluate it, you'll get 4 independent numbers. Add those numbers together, and you'll still get 180, or not 180 degrees, but just 180. So that's how we're kind of using the properties of summation. Now what we're going to be looking at here is okay, well, now that we kind of know what the properties of summation are, this is kind of still piggybacking on the idea of, can you write a sequence in summation notation? Now remember, summation, it's just going to be using the symbol sigma. Tripping over my tongue here. And the first index number here that we're going to be starting with, what this is telling you is that S sub 7 is we're going to take the sum of the first 7 numbers of this particular sequence. So since I'm taking the sum of the first 7 numbers, I'm going to say my first one is a 1, and my last index number would be a 7. Now, I'm going to replace the ends with a different variable. Now, that variable can be k, it can be j, it can be really any number, that it could be x. I just generally kind of steer away from using n when we're doing stuff like this, because n is generally accepted in mathematics to represent like an nth term. So if I say n is equal to 1, I'm saying, well, that's the first term of a sequence of numbers. If I say n is equal to 5, that's the 5th number in whatever my sequence gives me. So I kind of don't like using n here, so that's why I'm going to use k. But this part right here, where I write the sigma notation and I'm saying, well, we're going to do it from the first term to the 7th term, that's really all we're doing. So I would say k cubed minus 2k, or x or j or c or whatever variable that you wanted to start your index with. And in the denominator, I'd just say k plus 4. And if you want to, you could put the entire sequence in its own parentheses, but this is pretty much it. That's all the sigma notation is telling you to do. Now the next example is kind of asking you to do the same thing, but they're trying to make you, question yourself, well, what does it mean when it says the fifth partial sum? Well, that would be the same thing as saying S sub 5, meaning we're going to take the first 5 terms and add them together. So using my sigma notation, okay, I'm going to say, and I'll use K again. I'll start at the first one and I will stop at the 5th one. So that's really all the sigma notation is doing for the summation. And here I'd say K to the 3 over 2 power plus 4. And again, if you want to put the sequence in its own in a set of parentheses, if you wanted to, that would be fine, but I'm going to just leave it like, I don't understand why I keep getting gaps in some places on my board, but there you go. There's sigma notation. Okay. Now, the one thing that you do have to pay attention to is an example like what you're seeing here. This one is not asking you to say the sum of the first 9 numbers or the sum of the first 5 numbers. It wants to know the sum of the number of the numbers in the sequence that from the 5th one through the 9th one. So when I put my sigma notation here, at the bottom, my first index number is not going to be 1, it's going to be a 5, because that's where I'm starting to count at. I'm starting at the 5th one, and I'm stopping at the 9th one. And so then we would just have 3 and minus 4. And happy sigma notation, and that's pretty much it. So using sigma notation, we can identify some properties where essentially we're really looking at how we can factor a number out of something, so that way we can shorten, so we can say, oh, well, this times this is all that. It's just a way of simplifying how much that we have to write. And it's very helpful when we start doing expressions where the expressions themselves are kind of long. Okay, it's just a way of helping us to simplify things. And so far, what we've seen is a way of we're adding only a few numbers. And for what we've seen so far, if we're only adding a few numbers, these properties work really well. At some point, though, we're going to say, okay, well, what if I wanted to know the sum of like the first 100 numbers in a sequence? And this would work, but you would be writing a whole lot of numbers down. And so soon we'll show you how we would simplify that to not have to kill our hands writing 100 numbers each time we need to work out a problem. So any questions that you've had during the presentation here, make sure that you write them down. Any thoughts you want to clarify, again, make sure you write them down in your notes. And when you see me in tutoring or in class, please bring them to my attention. And as always, thanks for watching, guys. See you soon.